Hey Mustangs, welcome back to another edition of No Here No Problem. Rosenwald here, getting ready to talk to you guys about a brand new unit that we're going to be starting. This is chapter 8 of our pre-calc book, and this one relates to all things sequences and series. We're going to start off first with just kind of defining these, and then we're going to practice working with them. So let's get started with the fun. All right, so we are starting off first with just basic sequence and series properties and the rules of them and everything that kind of goes into it. Let me see if I can shrink this down here. All right, so sequences of series. So what you should be learning in this objective, we're going to talk about sequence notation and then how to actually write the terms of the sequence. And we're also going to use our calculator to do some of this as well. We're going to practice with how to actually use the calculator to write the sequence to make our lives much easier. We're going to use factorial notation. Good old, I should actually put just like a big old exclamation point right here. Factorial notation! We're going to use summation notation, which is our sum symbol, sigma. And we're going to talk about the parts of that. We're going to find sums of an infinite series. And then we're going to use sequences of series to model and solve real life problems. So let's get started. Sequences, by definition, it's a function whose domain is a set of positive integers. So what that means is we're talking about finding a list of numbers starting with usually a zero or, with either the zero term or the first term. So you'll notice here we say A1, A2, A3. Well, these subscripts are saying that we're referring to the first term. And then we're saying the second term and the third term. So first and second and third and fourth. And occasionally, what you're going to see in a finite sequence is you might see a zero being used instead, which is a way of just saying our initial one. So you'll all see it when we come into it, when we start dealing with these problems. You'll see occasionally there's a zero, occasionally there's a one. Sometimes they want you starting from the third. Try to think of it like if I went into a movie theater and I said, how many chairs are there in the movie theater? And I want you to start from the front of the theater, you would start with zero. But what if I was to say, I want you guys to go ahead and find the sum of all the seats that are in the theater. Let's start from the fourth row. Well, I wouldn't start with A3. I would start with A4 being the fourth row. So we'll get to some of those though. All right. So let's get started though. So writing the terms of a sequence is literally as simple as something you guys have been doing forever. If I gave you a problem, y is equal to 3x or 3, not n, x minus 2, and I said, go ahead and list out all the values that are going on here. What we're doing is I would take and literally put in a 3 times 1 minus 2, a 3 times 2 minus 2, a 3 times 3 minus 2. So don't get hung up when we're sitting here talking about an and 3n. When we're talking about n, we're just talking about terms. We're not talking about an xy coordinate plane. We're just talking about terms, which is why we don't use x and y for these. We're talking about numeric values in some sort of list. So if we look at this example here, we say we have a sub n is equal to 3n minus 2. If we take the first term here, which the script on this is a little wonky, this n right here is supposed to be down there, but this n is actually supposed to be in line with it. So it's supposed to be 3 and then like an n right here. But when we are doing this, what we're saying is the first term, so I would put in a 1 right here, is going to equal 3 times a 1 minus a 2. So that's what that first term is. We're just putting a 1 in for the n. For the second term, we put in a 3 times 2. For the third term, we put in a 3 times 3. And for the fourth term, we put in a 3 times 4. And our list of values that we end up with when all is said and done is going to be the 1, 4, 7, and 10. So if I said to you, list the first four terms, you would go ahead and say 1, 4, 7, and 10. Okay? I want you guys to notice what's going to happen with this one right here because we have a negative 1 to the n power. Let's see if it shows in this example here. It says write the first four terms of the sequence below. If we put in a 1, what's going to happen is we're going to have a 3 plus negative 1 to the first, which will be 3 minus 1. If we have a 2, we're going to put a negative 1 to the second, which will be 3 plus 1. We put in a negative 1 to the third, we get a negative 1 in there again, so it'll be minus 1. And then we put in a 4, we're going to get a negative 1 to the fourth. And what I want you guys to notice here is this, that we end up with a negative 1, positive 1, negative 1, positive 1. Start paying attention to this right now because you're going to see this pattern right here pretty frequently throughout this unit where it's saying -1 to the n power. And that is just a real quick shortcut to know that when we have alternating signs in a problem, so let's say you go like +4, -8, +12, -16. This tells you that there's going to be a -1 to the n power being involved in our problem in some way, shape, or form. Okay? So we can see, though, the first four terms of this are going to be 2, 4, 2, and 4, and it would just continue on doing this over and over and over and over. There's a rule in this unit called a recursive rule, and the notation is kind of wonky for people at first, but it's really supposed to be self-explanatory. That if I was to say to you, your first term in the sequence is 15. So if I was to make a list, my first term is going to equal 15. That's what this says when we look at this. My first term is 15. What this says over here in recursive notation is this. It says that my next term, so if you think about what k plus 1 is, it's saying whatever is k, we're going to just add 1 to it. So let's say that this is k. You might even say it is a sub n plus 1. So what this means is the next term. So if I put in a 1 right here, it's saying whatever my first term was plus 1, which will be my next term, is going to equal twice my first term. Now, it's a little confusing when you look at it, but again, my next term is going to equal twice my first term. Okay? And then we'll just continue on. I shouldn't say first term, I should say my previous term. So my next term is equal to twice the previous term. Okay? So here's what that looks like when we're doing this. So if we take this and we double it, it's going to equal 30. We take this and we double it, it's going to equal 60. We take this and we double it, it's going to equal 120. And again, to restate, my next term is equal to twice the previous term. So here's my previous term, here's twice it. Okay? Here's my previous term, here's twice it. Here's my previous term, here's twice it. Okay, you get the idea. That's recursive. It's always building off of the previous value. Always building off of the previous value. Okay? All right, so the next thing, factorial. This is not your first rodeo dealing with this, but factorial by definition is saying whatever the number is that's given to you, it's that number -1, -1, -1 over and over and over and over. So for example, if I was to give you 6 factorial, that's the same as saying 6 times 5 times 4 times 3 times 2 times 1. And it can technically continue on, but usually factorial stops at that spot right there. This is on our calculator. You should know where it is actually located, so let me show you guys. Factorial is actually going to be under stat. So if you go to stat, and then you go to, not stat, what am I saying? Math, and then PRB. So right where it shows PRB right here, which stands for probability, you're going to go over to probability there, and you'll see that there's an exclamation point down by number 4 in this problem. Okay? So get used to finding the exclamation point. We're going to be using it pretty frequently in this unit. All right. Let's go back to notability here. So 6 factorial, 6 times 5 times 4 times 3 times 2 times 1. So you'll notice that this term is always 1 less than the previous. And then this term is always 1 less than the previous. And so it generates this like recursive rule. It's always 1 less than the previous. Well, the formula for this is n minus 1 times n. Now I want you guys to see this in action, how this leads to a weird rule for us. Okay? The rule is 0 factorial is equal to 1. Now, how can this be? How can it be that 0 times anything is going to give us a 1? That just seems odd, doesn't it? I mean, that's not our first time that we've ever seen this. Well, if we were to say like 5 to the 0 power, we know that that's equal to 1. But what happens is that 0, whoopsie doodle, that 0 that's in there is established because of the fact of another rule, which actually is the quotient rule. The quotient rule says that if I had like 5 to the third and I divide it by 5 to the second, it's going to be equal to 5 to the 3 minus 2, which is just 5 to the first power. And you subtract these powers, right? Well, if I gave you this and I said 5 to the fourth divided by 5 to the fourth, we know that anything divided by itself is equal to 1, right? Well, if I used our previous rule we just did and I did subtraction, we get 4 minus 4, which means we have 5 to the 0, which we know is just equal to 1. So the 0 throws things off. Now let's look at it in action here, okay? Let's start with first this rule that 5 factorial is equal to 120. That's 5 times 4 times 3 times 2 times 1. And let's go on to the rule that 4 factorial is 4 times 3 times 2 times 1. And 3 factorial is 3 times 2 times 1. And 2 factorial is 2 times 1. And 1 factorial is just 1. Now, what's happening is, in the world of mathematics, we know that math is based off of a set of rules, right? And patterns. And we should see a pattern happening here that I go 20 to 24 is I divide by 5, right? And then I go here, I divide by 4. And I go here, I divide by 3. And I go here, and I divide by 2. Well, if I continue and I divide by 1, what's 1 divided by 1? 1. So we end up with a 1 here. And if we look at our rule here, we go 5, 4, 3, 2, 1, 0. 0 factorial equals 1. Now let's look at it from a different scope. Okay, same exact idea, but let's look at it from a different scope. Let's go ahead and just say that we know that 3 factorial is equal to 3 times 2 times 1, or just 3 times 2 factorial. Okay, we know that 5 factorial is the same as saying 5 times 4 factorial. We know that 10 factorial is the same as saying 10 times 9 factorial. We know that n factorial, this is the rule that we have, that n factorial is equal to whatever my initial term is. So this is the same, and then 1 away from it moving down. That's that n minus 1. So in this case, we have a 10, we have a 10, it's 10 minus 1. So what happens when I have this going on and I have 1 factorial times 1 minus 1 factorial? Well, when we look at this, we have 1 and the 1 in there, so the n's are the same, and we put in a 1 for n. And what's going to happen is right here, what's 1 minus 1 factorial? That's 0. Well, if this is a 0 and I do 0 times 1, wouldn't that just equal 0? But that's not what happens. It has to equal 2. A 1. There you go. Okay. So there's our property that 0 factorial is equal to 1. So let's look at some problems in these where we're talking about a sequence and we have a factorial involved. Okay. So for the first one, if we were to go ahead and put in a to the first, that means we're going to have 2 to the first over 1 factorial. So that's just simply be 2 to the, in this case, we're beginning with 0. They tell us to start with 0, so we're saying a sub 0. We're going to get 2 to the 0 equals 1. 0 factorial equals 1, so 1 divided by 1 is 1. We're going to get a to the first equals 2 to the first, and then over 1 factorial. And we can do this with then 2 to the second, 2 to the third, and 2 to the fourth. So whenever we start with 0, and it says that we're going to do 5 terms, you're going to end up with, if you notice right here, we end up with a 4 down here. Oops. We end up with a 4 down here, which is 1 less because you can count off. You got 1, 2, 3, 4, 5 terms going on here. Okay. All right. Continue on. Oh, let me show you guys really quickly how you can do listing of terms in a really fast, efficient way on your calculator. Okay. Go back to your calculator here. And you can do this on this calculator, and you can actually do it on Desmos, but I'm not going to, it's not super fast on Desmos, but I can show you guys. But what you're going to do is you are going to go right here on your calculator to where we're going to generate a list. Okay. So go second list. And what we're going to do is we're going to go over to math here. Nope, not math, operations. So we're going to OPS, and you'll see right here for option number 5, it says sequence. So we're going to generate a sequence here. And let's say the function happens to be like 2x plus 3. I don't know. You're going to just then assign the variable to be equal to x. Let's say we want to start from 0 and we want to end with 4. Okay, and we want it to increase by 1s. That's what that step 1 is right there. Go ahead and hit enter, and you'll see it actually lists the numbers for you, 3, 5, 7, 9, 11. Now, there's actually a faster way to do this. Just my opinion, it's a faster way, okay? If you skip this whole sequence deal, think about what we're doing. Earlier on in the beginning of this, I said this is no different than just doing y equals mx plus b, or just y equals some function, right? So what if we had a table of values that we can use? Well, we do. Look right here where it says table. So if we go to y equals and we say y is equal to 2x plus 3, and I say I want to get a table of values, you can go right here and hit second table. So second graph, and we can say we get, starting from 0, we get 3, 5, 7, 9, 11. You have your table of values right there. Okay? So that's just my opinion. Do it how you want. I don't care, but just know that there are ways of doing this that are quicker. Play around. You might even find one that's even faster. I don't know. All right, so summation notation. This is also known as sigma notation because that's the Greek letter sigma. Anytime you see this symbol, it's actually going to look exactly like this. So if you're doing an Excel spreadsheet, it's going to show this sum symbol. That means we're adding up things. So how does this work, and what is this symbol actually saying? Well, there's 4 parts to this that are really important that you have to do. Okay? The first part right here is the bottom of this. This is telling the person that's looking at it what number we're going to start with. So this says, in this case, when we're doing this, we're going to start with a 1. Okay? The value on the top says that's the number that we're going to stop with. So if I said let's put it to a 5, that means the last number in the series is that we're going to use a 5 in this spot right here. Okay? And then the other parts here, this is defining our variable that's taking place in the problem. So that has to be the same as the other letters in the problem. And then we look here, this is always going to be the rule to the problem. Okay? So what does this look like in action so you guys can come follow this? So here's what's happening, okay? And you usually will see different variables here. Like in this case, we're using an I because that I has to be the same as what's here. You might have an X, you might have an N, you might have an M. You can have all different kinds of things. But what's important is that you understand what these numbers represent here. This number right here is going to be the last number used when we're plugging in the series. And this number here is going to be the first number in our series. So the first and the last. Oops, the last, okay? So, and then what we're going to be doing is we're going to be finding the sum of all of those terms, okay? So this is what it says. So the first term in this, when we look at it, okay? I'm sorry, this is listing them out. So we're starting, like we said, we're starting with a 1. So that's the first value here. And we're going to end with a 5, which is the last value here. And then we've got all the values that go in between. So we got 1, 2, 3, 4, 5. We're just putting in a 1 for the I here, a 2, a 3, a 4, a 5. And then we go ahead and this is just a real quick shortcut here that we have 3 times, because we have a 3 in each one of these. We can factor out a 3, and we have 3 times 1 plus 2 plus 3 plus 4 plus 5. And then we end up with 3 times 15, which means that the sum of all these numbers is equal to 45. Okay? Take a look at letter B. So again, in this case, what we're going to do is we're going to start with the number 3 to be put in for our K, and we're going to end with the number 6 to be put in for the letter K. So if I start with 3, we're going to go 3, 4, oops. We're going to go 3, 4, 5, 6 for the values that we're going to be putting into our series. And we're just going to take all those values and just add all those together. So we're going to get 10 plus 17 plus 26 plus 37. So we're going to end up with 90. One of the things I want you to notice in this is going to help you later when we start doing formulas, is when you look at these numbers in our formula, the 6 and the 3, you'll notice that the difference of 6 minus 3 is equal to 3. So there's 3. But you always notice that the number of values in the series is always 1 more. So there's actually 4 that are in the series, okay? So like if you look here, there's 5 minus 1 is equal to 4. Well, if we look at the series, there's actually 5 numbers in this series. There's always 1 more than the difference between those. And again, that comes down to the fact that we go 3, 4, 5, 6. I mean, I'm counting 4 numbers there, okay? All right, so like if we looked at this one, we say 8 and 0. And if we look at 8 and 0, 8 minus 0 means that we have 8 terms, but there's always 1 more, so there's actually 9 in the series. And if we look at it, we can see that there are going to be 9. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9. Wait, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's a total of 9 in the series. And we're going to add all these together. There's that 0 factorial that we talked about, which is equal to 1. And we get 1 plus blah, 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 blah. And we get this value right here. Now, that number right there, does anybody know what that number actually is? E. That's actually our E value. Take a look at this if you don't believe me. I'm going to go in here and type in the letter E, which is right above the division sign. You get this. You get 2.71828. This is a formula. This is the rule for the sum of 1 divided by n factorial. And if you do this forever, you'll get the exact value of E. Okay? So kind of cool that you can actually see this value being put in place. You know, that the sum of every single number, infinite number, is going to end up equaling 2.718, which is 1 over n factorial. There you go. All right, so these are some rules for summation notation. You don't have to memorize these. It's more just kind of common sense. It's just extra rules for us to learn. But what ends up happening is if we have a constant here, the constant is just going to equal c times the n value that's out here. That's because, like, let's say I had a constant where it was like the summation of I is equal to 1, and we're going to go to 10, and not 10. Oh boy, I'll be here all day doing that. Let's say like 4, and we have like a 5 right here. That means and there's no n's. There's no I involved in the problem. So what this says that my series would be a 5, a 5, a 5, a 5, and well, that's it. So what ends up happening is we have a 5 repeatedly because it's a constant. We just add these together, it's going to end up equaling 20, which is the same as saying 4 times 5. Okay. You can play around with the other rules. They're all pretty self-explanatory as you play through them, but it's not necessary that you memorize them. Okay. All right, so let's get to what we call partial sums. Okay, a partial sum is when we're doing a finite series, which we just finished doing. When I say I'm going to do only the first 4 terms, or only the first 5 terms, or 6 terms, that's a finite series because I'm giving you a start and an end. But what about when we have an infinite series and we're looking at where we go on forever? How do we find these? Well, in 2 sections, when we do geometric series and arithmetic sequences, we're going to talk about what the sum is in an actual formula. For right now, it's more just intuitive. So when we look at this series, 3 divided by 10 to the I power, and they say to find the third partial sum. So they're telling us, let's take this series, and instead of going to infinity, we're going to change this to be a 3 because it says to the third partial sum. Okay, so what's going to happen is we're going to have a 3 divided by 10 to the first, 10 to the second, and 10 to the third. We'll add all these together, and we end up with 0.3, 0.03, and then 0.003. And when you look at this, you can see that this equals 0.333. Now, if I continue this indefinitely, this is the sum of the first 3 terms. It's 0.333. What happens if I decide, let's not do the partial sum. Let's do the entire thing, just forever, right? Well, if we do it forever, it's going to end up being 3 over 10 to the first, 10 to the second, 10 to the third, and so on forever. And when we look at this, we get 0.3, and then 0.03, and then 0.003, and then so on and so forth. And if I continue to do this and I add all these together, this is where we end up with 0.3 repeating. And what do we know that 0.3 repeating is actually equal to? It's 1/3. So 1/3 is actually what happens for, if we were to say, like, what's the limit as I approaches infinity? It's 1/3. Okay. All right, a couple more problems to work through here. Compound interest, nothing new for you guys. If an investor deposits $5,000 into an account that earns 3% interest compounded quarterly, the balance in the account after n quarters is given by, we should know this formula. It's, that whole A equals P times 1 plus R raised to the n. And we modify it by saying n times t, and we divide this by n, representing the number of times that it's actually taking place that we're earning the interest, right? So we say divided by n. So our formula when we look at this is going to be, when we plug all the values in, we're going to have 5,000, 1 plus, we're going to have 0.03, because that's the interest rate, and it's divided by 4 because it's being done quarterly. But it says here each quarter. So it's n quarters. That's why we don't have n times t. It's just each quarter we're going to do it. So 0, 1, 2, and so on. So n quarters, we have this. We're not saying for years. We're just saying quarters. Okay. So it says to do this, and go ahead and list out the 3 terms in the first 3 terms in the sequence. So we're going to use 0, 1, and 2. And then we're going to find the balance in the account after 10 years by computing the 40th term. That's because there's 4 quarters in 1 year. And if we're doing it for 10 years, we're going to do it for 40 times. That's where that whole n times t would come into place here. Excuse me. Whew. So if I say, let's find the 0 term, we're going to put in a 0. So 5 times 1 plus 0, 0.03 over 4 raised to 0. So at the beginning, we have 5,000. That should make sense, right? Hang on. Never mind, fooled you. It went away. All right. After the first quarter, so after the 25% of the year, 1 quarter in, we now have $5,037.50. All right. After the second quarter, we're going to have $5,075.28. Okay. So that was part A, was finding those first 3 terms. In the part B, it says to find the 40th term of the sequence, which is A40. We're going to plug in a 40, and we end up with $6,741.74. So that means that after 10 years of getting money every quarter, we're going to end up with this much money. Okay. That is it, I believe. I think I've covered everything. If you have any questions, though, please reach out. Until next time, you guys stay safe, stay responsible, and don't forget to like and subscribe to my channel, and you take care, okay?